Okay, my husband always says start with a joke, but that doesn't mean losing your shoe on the way up. But it's been that kind of a day, and Brother Guy will attest to that. The poor Brother Guy spent 5 hours waiting for his flight from Chicago, so we have to really give him a warm greeting when he's up here. I'm Rita Tonetti, Development Director at Manresa, and I welcome all of you. I am so pleased that you could all join us tonight. I feel like I was selling tickets for Elvis or something, that they were in such demand. Right up to the last minute when I had to run out the door and say, enough, I can't do anymore. So it's going to be a wonderful evening, and I would like to just add a couple of things. Of course, we all know what these are. We all know what we're supposed to do with them. So if you haven't done it yet, please do that. And I also would like to add a couple of other suggestions of things to do at Manresa that Father Daly didn't mention. We have a series of concerts that we do 4 times a year at Manresa. They're always a wonderful event, and we have one coming up in December on the 6th. Which is a Sunday, and there's always an afterglow. It's a beautiful afternoon. It's, of course, going to be seasonal music this time, the Madrigal Singers. We'd love to have you there. And for the ladies, there is an Advent tea on December 7th, which is a Monday. It starts at 1 o'clock, and we'll have a reflection by Denise Anderson, our head of women's programs, and then we will have a delightful tea with real teacups, and we'll practice putting our little pinkies up. So I heartily recommend that you all look at some of the things that we have outside on your way out, or check our website when you have an opportunity, and join us whenever you can. We'd love to have you join us. So let me do the honors of introducing our speaker, who is waiting with bated breath over there. Brother Guy is, as Father Daly said, part of the Society of Jesuits, Society of Jesus, better known as Jesuits. He's locally born and bred. He went to Queen of Martyrs Catholic Elementary, and then he went to what is called the High, University of Detroit High School, and we are thrilled that he was able to come back and share his knowledge with us. I saw him speak here, I don't know how many years ago, it could have been 10, and I've been looking forward to an opportunity to hear him again ever since then. So when I was able to host this, I was absolutely pleased as I could be. Brother Guy this year was named director of the Vatican Observatory, and last year he was in town, and we had a chance to chat with him because he was here to pick up the Carl Sagan Medal, the first cleric to ever be offered that. And when they made the announcement, they said that he occupies a unique position within our profession as a credible spokesperson for scientific honesty within the context of religious belief. And so let's hear what he has to say on that subject.
This really is a homecoming. I mean, I recognize a few of the faces in the audience, and which is amazing, because it's been 50 years. But I would ride my bike to Cranbrook and take part in a lot of the different programs that were offered for crazy young kids in the 1960s, of which I was happy to be one. This is going to be a science and religion talk. That's kind of the theme. And before I get into that, I know a lot of people are curious about the Vatican Observatory. So since you've already seen one video clip, why not another one? This one, rather than listening to me, you can listen to somebody who's much more eloquent than I am.
Both science and religion are conversations about the universe. They're ways of learning how we interact with this universe. It's not simply a question of, is there a God? But there is a God. Now what do we do? It's not just a question of, there are a bunch of stars, but rather, why are there stars? How do they work? How does that tell us how things work here on Earth? The interaction that I see in my own life is that religion gives me the reason to do the science.
Back in the papacy before Francis was Benedict, and one of his lines in a final elocution to the fathers of the general congregation was, "Go to the frontiers." Well, there isn't much more frontier than 3.7 billion years away.
The first official interest of the Church for astronomy started in 1582 with the reform of the calendar. Then in 1891, Pope Leo XIII wanted to have an observatory to show that the Church is not against science, but the Church promotes good science.
They start out by having telescopes on the Tower of the Winds, and then on the walls surrounding the Vatican. As the city lights grow, and as the Italian government gives them back the territory out in Castel Gandolfo, in the 30s they build new telescopes on the roof of the Papal Palace in Castel Gandolfo. Best telescopes of their era in the 1930s. By the 1980s, light pollution makes those telescopes unusable, so we build a new telescope in the dark skies of Arizona.
I'm Father Jean-Baptiste Kikwaya Eluo. I'm working in 3 projects. The first one is NEOS, Near Earth Object. So what I'm doing with NEOS is just observe them using our modern telescope VAT. The second project is meteors. I worked on very faint meteors, what we call shooting stars. And the third project is a set fireball network. They will have 4 cameras here around Tucson, so that actually we can monitor any fireball getting into the Earth atmosphere in the region.
This telescope, the Vatican Advanced Technology Telescope, it was the first of the new technology telescopes that has been considered pretty much the norm now in developing telescopes. With the advance of computer technology, we have the capability of bringing that advanced technology directly into our telescope. So it's an expandable, it's almost like it's a living machine, so it can grow as technology grows.
It is still very important to maintain scientific research at the Vatican, simply because there is still a lot of confusion about this relationship between science and faith. We are not out here trying to prove the existence of God by looking through a telescope. That's not what we're doing. But we can say that if we want to obtain any reasonable results looking through that telescope, we need to do it embracing a certain work ethics that is, in fact, the same work ethics that the Bible itself tells us through commandments and through the Gospels to embrace.
Human beings look at the stars and wonder. They want to know, what is that? What is that about? How do I fit in? They hear about the moon landing, and they want to know, what was that like?
Very well.
If we're part of the human race, we're part of the race that went to the moon. We're part of the species that looked at the stars and wondered, what the heck are those things? Looking at the sky reminds you that there's more to the universe than what's for lunch. What's more, if you believe in a universe that God so loved that he sent his son, then not only are you going to want to study the universe because it's kind of cool, it's an act of worship. It's an act of getting closer to the Creator and getting closer to a universe, as St. Athanasius said 1,500 years ago, was cleansed and quickened by the Incarnation. Then, doing science is an act of worship.
That phrase, doing science, When I was a student, we never heard it phrased that way. Now some of the kids who are talking about it will say, I'm doing a science, is a kind of a funny way of describing. But what does it mean to do science? This is a science and religion talk, but I suspect more of you have been in a church than have been in the lab. Also, it's a talk where you've got an astronomer here, and so if you can have an astronomer, you ought to have some pretty pictures. So let's have a pretty picture. And let's do some science with it. Now, I like this particular picture because I would show this picture to my students when I was in the Peace Corps 30 years ago, when I was in Kenya. And the kids loved it because, of course, they could see themselves. You recognize Africa, and if you don't know where Kenya is, right there. And after I'd show the pictures and they'd all get really excited about seeing themselves, I'd say, all right, when was this picture taken? And they'd look at me funny like, what do you mean? So I said, oh, first of all, in Kenya, is it daytime or nighttime? I'll ask you. Is it daytime or nighttime in Kenya when that picture's taken? How do you know? It's in the sun. All right, is it the morning or the afternoon? Is Kenya about to go into the shadow, or has it just come out of the shadow? How many people think it's the morning? How many people think it's the afternoon? How many people are afraid to guess? Where's the sun? Over there. Which means if you're standing here, you're looking to the west. So it must be afternoon. All right. What season was it when this picture was taken? You know how the seasons are caused by the tilt of the Earth? Trick question. Kenya's on the equator. All my students immediately said, it's the rainy season. Which you can tell because it's covered with clouds. But, northern hemisphere, what season is it? Northern hemisphere, is it winter or summer? The equator is kind of running this way. And if you look at Europe, you'll see Spain is in beautiful sunshine, Italy is in beautiful sunshine, England is exactly covered with clouds. Summertime, definitely. All right. What day was this picture taken?
Sunday.
Well, at least what week?
Week.
Any guesses? Could he give you a year even?
69.
Say again?
69.
Why do you know it's 69? That was not 30, that was more. That's when Apollo 11 came. When did Apollo 11 land on the moon? July 20th, 1969. Now, remember I said I showed this picture to my students more than 30 years ago. We didn't have good television cameras that far away from the Earth. We didn't have good television cameras. That picture was taken on film with a Hasselblad. So it had to be taken with an astronaut who was on their way to or from the moon. And how many missions were there that were during the summertime? 2, actually. Apollo 11 and Apollo 15. And I happen to know that Apollo 15 was on a different orbit that gave you more a view of the South Pole and not so much the equator like that. So if you said 1969, if you said July, you're absolutely right. Now, you're going to say, wait a minute, everything else I could get from the picture, that last bit was cheating. There's no such thing as cheating in science. Any way you can get the data. You're going to take that and you're going to apply things that you've learned elsewhere to the data that you got here. But notice what else we've done in this exercise. We've taken a picture that you've seen a million times, and we've started pulling out of it a story. We're starting to pull out of it questions to ask that we can answer. You're never going to quite look at that picture the same way again. And that's what science is. It's taking something that anybody can read, anybody can see, anybody can experience, and learning to ask questions to put it in a story. It's that human aspect that means that you can't have a computer doing science. Science is something done by a human being. Let's try it again. Planet Mars. This was one of the best images of Mars back when I was a student in 1971, 72, taken with a telescope from Earth. If you've actually looked at Mars through a telescope with the naked eye, you can see it much better than that. The trouble is that the Earth's atmosphere blurs things up. But every now and then, for an instant, it stops blurring, and if you're very sharp and you're paying attention, you get this momentary, oh my gosh, it's sharp as anything, and then it blurs up again. But for the most part, if you're not, a person with super eyesight, you're standing at a telescope, you're looking through an eyepiece. If it's a good telescope, it might look something like that, a lot smaller, but it's not big. More to the point, if you're actually outdoors, you have to do astronomy in the outdoors. You've got to, you can't have windows. It's got to be open to the air. It's usually cold. You're usually on a mountaintop. Usually the air is really thin. You're lucky if you can stay awake long enough to get that. What are we looking at here? Well, got white things at the north and the south. What could those be? Ice caps. And then we've got this bright region and the dark region. Now the bright region is kind of orangish red. What's the color of the dark region? And you get all sorts of different answers. Some people say that it's brown. Some people say that it's maroon. Some people say that it's kind of an olive green. Well, here's the interesting thing. Mars, like the Earth, is tilted when it goes around the sun. It also has seasons. Sometimes the sun is shining in the northern half. Sometimes it's shining in the southern half. When the seasons occur, the caps get smaller. As the caps get smaller, presumably the water melting, right? The dark areas grow. Now, if you look very, very carefully at those moments of instant, you will actually see lines, and not only do you see them, but a couple of other people have seen the lines in the same place. And now that we've got modern telescopes, the lines have all disappeared. They were optical illusions. But they didn't know that at the time. What would be more logical than to put all of these facts, all of these observations into a story? The cap shrinks as the water melts. It goes rushing down these channels and makes these dark olive green areas grow. So we've got evidence of life, and not only that, but with the canals, maybe intelligent life. Because notice the one thing you don't see on Mars compared to the Earth are a lot of clouds. Though you've got the caps, otherwise it looks pretty dry. So if you were trying to keep a civilization going on Mars, you'd need the canals. You'd need the water coming from the poles. It's all beautifully logical. And it's all perfectly wrong. It's wrong for a lot of reasons. Turns out the caps are actually not made of water. They're made of carbon dioxide. They're dry ice. There is some water there as well, but the main caps are dry ice. The dark areas are not olive green. They're actually gray. And all of the colors that you think you see is just the eye's optical illusion of having this bright red region next to it. You want to have the gray area so to be the complementary color. And yes, they do grow with the seasons. It's because there is a fine red dust that covers the gray rocks. And when the carbon dioxide caps shrink, it pumps all of this carbon dioxide gas into the atmosphere, creating winds that blows the dust off of the gray rocks. That also is science. Because once you've got a story, you don't stay, well, that was a cute story, I'm going to live with that. You keep asking yourself, can I prove it? Can I demonstrate it? Can I get more into it? Can I come up with alternate stories? You're never going to be satisfied with one. You're never going to be satisfied with one description or one explanation. You're always going to be wanting to dig deeper. You're always going to be wanting to ask new questions. If you don't have new questions, then you're not going to get any more grant money, you know? But the point is this. Science, because it's always coming up with new descriptions, is never dealing in proofs. If anybody ever tells you that such and such has been proved by science, what they're proving is that they don't know what science is. Science doesn't prove. Science describes. For example, say you see a panel like that, and it's in a big auditorium, and you want to know which of those switches controls the lights in the auditorium. So you flip the switch to the top right, and all the lights go out. And you say, okay, now I know what switch it is. That would be a terrible proof if you were a philosopher or a mathematician. How do you know that somebody at the other end of the auditorium didn't just happen to flip the right switch at the same time? And it was a terrible coincidence. Coincidences do happen. There was a guy I knew who was showing a VIP around the baseball stadium in Milwaukee that's got this retractable roof, and he knew that they were going to uncover the roof for a baseball game at exactly 7 o'clock. So he brought the VIP along and he handed him his television clicker and said, click here at 7 o'clock. You get to open the roof. To a mathematician or a philosopher, flipping the switch and seeing the lights go out is far less than a proof. But to a scientist, that's what we start basing our assumptions of what proofs are. And if it turns out to just be a coincidence, and you do it over and over again, and you're managing to actually match the other person on the other side of the room, and you've got this really long string of coincidences, well, maybe a really long string of coincidences is what we call a scientific law. The fact is, we report our results using the laws of statistics to have a way of trying to estimate just how confident we are. And if your statistics tell you that this has a 99% chance of being true, it means there's a 1 chance in 100 that it's a coincidence, that it's not true. And if you've got thousands of different experiments, a lot of them are going to turn out to be coincidence. You never know ahead of time which of those 100 or which of those 1,000 is the coincidence. The history of science is littered with people who took good data, came up with great explanations, and they were fooled because what they thought was the growth of water and trees was actually the coincidence that dry ice blowing off dust gives you exactly the same result. But notice what else this tells you about what you have to be a scientist, the internal attitude you've got to have. First of all, you have to admit you don't know it all. You have to go in with a lot of humility saying, I don't know, let's find out. There are cultures, you know, have you ever tried taking a taxi cab in Tokyo? The taxi driver can never admit that he doesn't know where you're asking him to take you. He will drive in circles before admitting he doesn't know, because it's a way of losing face. You can't do that and be a scientist. You have to be willing and thrilled to make mistakes. My dad, teaching me here when I was, going on to U of D High and going down Woodward Avenue every day, we had these fantastic philosophical conversations that I still remember. I can repeat them back to him now. He's 97. He's forgotten them. But he said, knowledge is like an island. The more you know, the bigger your island. But the shoreline is the boundary between what you know and the ocean of what you don't know. And the bigger the island is, the longer the shoreline. So the more you know, you really do know, but then you're also aware of what you don't know. And so if you think you know it all, it's because your island is really small. It means that if you're aware of what you don't know, you're constantly testing the things that you think you do know. That's why you do experiments. That's why you continue to ponder. That's why you continue to come up with new ideas. And that means that the books keep getting updated. Now, in 1930, when the Vatican Observatory moved out to Castel Gandolfo and we suddenly had room, the Vatican libraries decided that was their chance to get rid of their uninteresting surplus modern science books. To them, modern is anything printed with a printing press. So we've got a picture, a copy of the second edition of Newton's Principia. We've got a second edition of Copernicus. The interesting thing is this. They're wonderful books. They're books that changed history. But I would challenge you to find 10 physicists who have ever actually read Newton's book. For one thing, it's written in Latin. For another thing, even in translation, the questions he's asking aren't interesting questions anymore. And the language that he's inventing has changed and morphed, and those words don't mean what we used to use them to mean. Put it this way, if your son is taking high school biology, he's not going to use the same textbook that his mom used when she took high school biology 30 years ago. But if your son is taking a course in Plato, he might use the copy of Plato you had in college that has all your annotations in it. If, your daughter is going to be taking a course in Shakespeare, she would probably like to have the copy of Shakespeare's works that have your notes in them. There is a difference between books like books of philosophy or books of literature that are timeless and books like science that you have to throw away after 2 or 3 years. Now, does that mean that science is without content? No. Because the way we approach the science is good from generation to generation, though we learn new techniques. But the nature of asking the questions and engaging in the conversation is true. It's simply that we have new ways of asking the questions. And the science is about the questions themselves as much as the data that the questions are made of. Notice another thing. There's a difference between the questions and the data. The Mars that the Hubble Space Telescope looked at is the same Mars that Percival Lowell looked at when he came up with this crazy idea of canals. The planet hasn't changed. Our way of thinking about the planet has changed. I gave a talk here 10 years ago about Pluto, and a little kid right here came up and said, but what happened to Pluto? Nothing happened to Pluto. But everything happened to us in the way we thought about Pluto. In other words, science depends on the scientist. Personal, non-rational, human urges influence not only what we decide to do, but how we go about doing it and how important we think what we're seeing actually is. For instance, think of a pendulum. Back and forth, and back and forth, and back. You're getting sleepy. Now, if you're Aristotle, you saw pendula, and what you noticed is that they eventually come to rest pointing straight down. And out of that, you derive the principle that all things in motion eventually come to rest, and that there is a natural ending place for everything that started out in motion. And that's one of the principles of Aristotelian physics. If you're Galileo and you're looking at a pendulum, you notice that even as the swings get shorter, the amount of time it takes from one swing to the next stays constant. And you say, that's an interesting principle that Aristotle never noticed. And if you're Isaac Newton, you're going to say, actually, the pendulum would continue forever with the same arc, except that there is friction in the pivot point. And if you oil the pivot point, you can make it run longer, or if you add a little something like a falling weight to keep it moving against friction, you can keep it going forever. And once you have all of those different ideas of the pendulum, it's the same pendulum. But if you've got Newton's ideas, you can construct a clock with Galileo's idea of the pendulum so that the clock keeps good time, but Aristotle reminds you, you've got to wind the clock every day. All of them have a point. All of them are describing what they saw, but all of them are also abstracting from what they saw the way that a video camera looking at a pendulum couldn't do. When we were kids, we learned the scientific method. Notice a problem. Devise a hypothesis. Test it with an experiment. Yeah. I've never known anybody who's ever actually done science that way, by the way. Most scientists I talk to say, yeah, that's what you teach in the 5th grade. There has never been a Nobel Prize that was won by doing that. But it's a nice abstract way of describing what goes on in science. Let's say it's true. How did you choose which problem to work on? Where did that hypothesis come from? You probably dreamt up a dozen different hypotheses, but you only had time to test 1 or 2. How did you choose which ones were the ones worth testing? Take an example. Is there life on Mars? We know that Percival Lowell's arguments about the growing green areas, that doesn't work, but that doesn't prove there isn't life on Mars. Is there now, has there ever been, card-carrying life on the red planet? Oh, who cares? Actually, I can cook up half a dozen reasons why finding life elsewhere might be interesting to advance our knowledge of biography, so you can, get better drugs, you can have better agriculture, whatever. In the 19th century, Michael Faraday was working with electricity in his lab, and the story goes that Disraeli comes into the prime minister. He says, "Mr. Faraday, of what possible use is electricity?" And Faraday goes, "Mr. Prime Minister, someday you'll put a tax on it." But that's not why we do it. That's not why we're fascinated about if there's life on Mars. That thing inside us that makes us fascinated, it's where we care. It's what motivates us. It's part of what gets us up in the morning. I say that's connected to where your religion is. Okay, granted that you care about it, how do you go about looking for it? Well, you can try to go to Mars, and we've sent things to Mars. We've never been able to see anything in Mars that absolutely proves that life is there, but we've seen things that are not inconsistent with the possibility of, which is not quite the same thing as a proof. You can do images from above, and you can see that Mars has volcanoes. You can see that Mars has volcanoes that have emitted water. You've got clouds. You've got carbon dioxide. You've got all the ingredients. You saw even these little streaks going down. NASA announced just a couple of months ago, they've discovered water on Mars for the 12th time. And what they had done was looking at some of those streaks, they saw them changing from one image to the next, and they saw associated with them the sorts of things you would expect for water that had evaporated, and this is what would be left behind. Again, it's better than the not inconsistent with argument. It's all the way up to the consistent with argument. We're still arguing about it, though. We had this meteorite from 1984, Allen Hills 84-001, collected in Antarctica. I was in Antarctica collecting meteorites. That's me there. I did not collect this meteorite. This one was picked up a few years before I was there. And in it were 4 lines of evidence of her life, that there were these little things that look like fossilized bugs, and there is polycyclic aromatic hydrocarbons, and there are tiny crystals of sulfate, just like the kind that you see around bacteria in terrestrial rocks, and there are tiny magnetite crystals of exactly the right shape and purity that you would have inside bugs that use little magnetite crystals as internal compasses to let them know which way to swim in order to find sunlight, if the planet has a magnetic field, which it turns out back then Mars did. And the cool thing is, when beforehand, when you had asked, what are the signs of life, these are the sorts of things you'd look for. Here's the rock with all the things you were going to look for, and everybody who looked at it goes, I'm not convinced. Because I can explain every one of those things with stuff that has nothing to do with life on Earth. I can get little bug-shaped things in Columbia River results that have nothing to do with bacteria. I can get polycyclic aromatic hydrocarbons out of the snowmobile that they drove up next to the rock to collect it. There are non-life ways of getting all. Now, we learn in philosophy of science, Occam's razor. Given different hypotheses, you choose the one that's simpler. So you tell me, is it simpler to say that all of these different things in the rock can be explained by one hypothesis, life, which seems very, very otherwise extraordinary, or that there happened to be a coincidence of four things that all hit the same rock, all of them giving you one of the lines of evidence of life? And it's up to you to decide which is simpler, because a friend of mine, Tim Swindle, who's a meteoriticist, went and asked scientists in 1997, the year after this came out, do you really think this is life or not? And half the people he asked said, you've got to be kidding. No way. It's what, one chance in 10. And the other half said, well, it's interesting. It's certainly worth looking at. There might be a 1 chance in 10. They even came up with the same fake, 1 chance in 10 that came out of nowhere, but had completely different attitudes about whether they're going to spend a couple of years studying this rock or whether they're going to say, I don't need to waste my time. Science is done by scientists. Scientists are people. People make choices about what they're going to do with their lives, what careers they're going to follow, what schools they're going to go to, which experiments they're going to perform, who they're going to choose to be their thesis advisor. The philosophers of science tell us that every experiment is theory-laden. In other words, when you're designing the experiment, you already have an idea in the back of your head of what you're expecting to see. If you didn't have that idea, you wouldn't know to see it when you saw it. There's a great story about Albert Einstein. You notice the guy with the wild hair. In the 1920s, after he'd come up with his theory of general relativity, a couple of scientists in Cambridge devised a test for general relativity. And they announced to the world that general relativity failed their experimental test. So what do you think of that, Mr. Einstein? And Einstein's reply was, well, they screwed up the experiment. How can you say that? You have a hypothesis, you devise an experiment, and he goes, no. God is subtle, he's not malicious. My theory is so beautiful and so elegant, basically, he's saying, that it couldn't not be true. Terrible science, right? Well, he was right. The guys had screwed up the experiment. And the idea God is subtle was actually used as the title of a wonderful biography by Pace. Subtle is the Lord. The argument in many cases comes down to an aesthetic one. Is the description, is the theory an elegant theory? And if your idea of elegance is, Elvis painted on black velvet, then you're probably going to have different scientific choices than someone who has a different sense of elegance. But that sense of elegance is your moral compass when you decide, I'm going to do these experiments and not those experiments. Incidentally, the other guy in the picture, the guy with the familiar-looking collar, also has an MIT ring, or at least went to MIT. They didn't have rings yet. He had 2 doctorates, one from Louvain, one from MIT. He was a mathematician and an astrophysicist, His name was Georges Lemaitre, and he was talking to Einstein because he was able to read the mathematics of Einstein's general relativity and determine that by those mathematical equations, he could see the universe had the possibility to expand, and if the universe was expanding, number one, you ought to be able to observe it. Thank you, Mr. Hubble. And number two, in the past, space itself must have been much smaller, but the energy content was the same, so everything would have been much hotter until you could go back to a 0 point where things were so hot that they were almost at an infinite quantum state, and all of space was combined into one point that he called the cosmic seed. Well, he was working as a postdoc with Arthur Eddington, the fellow who had measured the twist of light due to Einstein's predicted bending of space-time. He published this work, and the British cosmologists of the day, other than Eddington, were furious. A fellow named Fred Hoyle gets on the BBC and starts making fun of this theory. He starts calling it, Father Lemaitre's Big Bang theory. The Big Bang was devised by a Catholic priest. What happened is that after the Big Bang theory came out, Pope Pius XII, who was something of an amateur astronomer, gets up and says in public, "Isn't it great that the scientists are now talking about a universe that has a beginning point, just like in Genesis?" And Lemaitre goes, "No, don't do that." Number one, it's a scientific theory. 1,000 years from now, we'll know where it's wrong. Number two, that's not why I came up with it. It's in the data. And number three, that's actually not what we mean when we say God's a creator. Little side thing here. About 4 years ago, Stephen Hawking came up with a book saying, "I figured out how the Big Bang occurred. You didn't need God to set it off. It was a quantum fluctuation in the zero energy gravity field. So there's no need for God." Actually, if you think of it logically, he's assuming that God is the thing that starts the Big Bang. Then he says gravity is the thing that starts the Big Bang. Therefore, it's not that we don't have God, it's that God must be gravity. By that logic, maybe he thinks that's why Catholics celebrate Mass. I can see which of you have taken physics. It's an important thing to remember that creation out of nothing is creation by a God who is outside of space and outside of time, and the creative act doesn't occur once 13.8 billion years ago, but occurs at all times. And that the nothing that God creates out of is not just a vacuum, but the nothing also doesn't even have the laws of physics, doesn't even have a vacuum, doesn't even have space and time. The God that Stephen Hawking is disproving is a nature God, as much as the Zeus throwing a lightning bolt was a nature God. I don't believe in nature gods. I think that lightning follows a path because it follows the laws of physics, not because some nature God threw the bolt there. There's a lot of gods I don't believe in. In fact, I only believe in one more God than Stephen Hawking. On the other hand, go back to Lemaitre. The British scientists mostly rejected his theory because they felt it was inelegant. A theory that has a starting point seemed inelegant to them. Whereas Lemaitre, having been raised in Catholic theology, was comfortable with the possibility of a starting point, whether or not he thought he had proved it. His sense of elegance was different from Hoyle's sense of elegance. Incidentally, Hoyle and Lemaitre finally met at a scientific meeting in the 50s in Rome. They became best of friends. They wound up going on vacations together. Now, Hoyle was still very anti-clerical and didn't believe in the Big Bang, except when more evidence showed that his alternate theories didn't work. And at that point, in the late 60s, he sort of begrudgingly said, okay, you were right. Because he was a good scientist. But this does raise the question then, if your ability to do science depends on elegance and your sense of elegance, what do I mean by elegant? I would say there's two traits that an elegant theory has to have. It's got to be beautiful, and it's got to work. Now, I'm a kid from Detroit, so let me talk about things that are beautiful. MG was a beautiful car. Anybody here ever own or drive an MG? Didn't work. They say the lighting was by, Lucas, Prince of Darkness. It was a mess to maintain. Beautiful, but a mess to maintain. Now, the car I actually wound up driving when I was a kid was this guy. It worked. Was not beautiful. Not elegant. What would I say was an elegant car? Well, maybe this guy. At first it seemed ugly, but you began to appreciate the things it did. You got used to the way it looked, and it had a certain form follows function beauty. Sometimes it takes time to recognize elegance. There are lots of examples of elegance besides cars. There are lifestyle choices that look really flashy but don't work. You're going to run off to the South Sea Islands with a movie actress. Wow, wouldn't that be great? It would be great for about 2 days, and then the paparazzi show up, and then she's running after the next guy, and suddenly, you're husband number 3 in a string of 12. You could, on the other hand, be too practical. Never give yourself a chance to enjoy yourself. Like the poor guy who is, again, opposed to Harry Potter because it's not serious enough and it's not science. Give me a break. And actually, it is science. He's really describing MIT, The universe is filled with joy. And if you deny the joy, you're denying your data. The universe is filled with beauty. To deny beauty is to deny the data of reality. Okay, so beauty is a part of elegance. What's beauty? It's in the eye of the beholder, of course. You know what a mini Helen is. It's a quantity of beauty sufficient to launch one ship. I have friends who have a hard time because you can't weigh beauty, you can't quantify beauty, you can't measure it. They almost want to say that beauty doesn't exist. But even rationality is a human creation. Consider the syllogism that goes, all men are mortal, Socrates is a man, therefore Socrates is mortal. How do you know all men are mortal? How do you know Socrates is a man? And where is it in your brain that allows you to say this means that Socrates is mortal rather than meaning that all men are Socrates? Try teaching logic and you realize that's not such an obvious step until you get used to it. Each step requires a little spark of insight. Each deduction is a wild leap from one place to the next. Logic is only our way of making the leaps short enough and small enough that most of us can follow along. But usually what happens is when you have an insight, you've made a huge leap, and then you spend 10 years trying to assemble the stones so that other people can see what you did without having to fall into the river. Logic has to be taught, just as beauty has to be taught. And it's taught by experience, it's taught from example. Everybody here ever take freshman physics? What do they make you do? sample problems, always sample problems, so that you get used to the way the physics works. You never really understand physics, you just get used to it. I have a physics teacher, a chemistry teacher, who the first day of class has a PowerPoint that explains how to juggle. And after everybody's gone through, you understand slide number 1, you understand slide number 2, you understand slide number 3. All right, get up here and juggle. You can't. There has to be an experience, there has to be a practice effect. Where else do we find sample problems? The parables that Jesus teaches. They're sample worked out problems so that we can get a sense of what it looks like to live in the kingdom of God. Too many people in our culture, and I don't just mean the scientists and engineers, but those of us who have been raised in 21st century American culture, don't understand that you find real, certain truth in poetry. Truth that can't be expressed in any other way except in poetry. At MIT, there are 2 big metal sculptures near each other. One is a Calder Stabile, which is gorgeous, and every kid at MIT loves it. And another one is a really ugly piece of sculpture called Transparent Horizons by an artist who hated technology, and why they bought this from her, I don't know. And no kid on the campus has probably taken the kind of course you need to understand modern art, but they know that they love this one and they hate that one because it's communicated brilliantly. Even if you disagree with that artist, she's a brilliant artist because she communicated how she felt in a way that everybody gets and that words couldn't describe. Even Newton's law of gravity is a poem. It's a metaphor. It's saying the path of a falling apple is like the solution to this equation. And by saying that, you're ruling out, well, what happens if the wind is blowing the apple? What happens if you're on a different planet? What happens if a black hole just happens to be swooshing by? It's a simplification to get at the essentials. That's what a poem is. And it's a way of giving a universal image that anyone who gets into it can understand, just like a poem is. And which is incomprehensible if you don't spend the time to learn how to read it, just like a poem. That's why people who insist on a literal reading of the Bible, as opposed to a scientific reading, they don't understand what the Bible is. They don't understand what science is. Science books get thrown out into the trash every 5 years. Are you going to throw the Bible into the trash every 5 years? It's not that kind of book. It's a kind of book like Plato and Shakespeare. It's a book that's full of truth, like Plato, like Shakespeare. And even people who get upset with the idea that something might be symbolic, well, that means it's not real, even symbols are symbols because they stand for something that is real. Every letter, every littera, that's where the word literal comes from, is a symbol. Every word is a symbol for a concept that otherwise we would not be able to hold and grasp and do anything with. A good choice of symbol, an elegant choice of symbol, is one that does a good job of communicating its truth and its beauty. Mathematics can be that kind of symbol. It's powerful because it's unambiguous. It's powerful because it has a certain predictive power. It's powerful because actually mathematics can be beautiful. But there's a lot of science that's not done with mathematics. I was a geology major. You look at the different forms on the earth, and then you look at the real rocks, and there's no mathematical way I can tell you that it's number 3 and number 1. Either you look at it and you see it, or you look at it and you don't see it. Which reminds me of one of the grand laws of physics, one of the grand laws of science. I would never have seen it if I hadn't believed it. You go to a road cut with a physics professor, and the physics professor, or the geology professor, and the geology professor starts telling you the history of all the rocks and what happened to the earth there, and you're going, yeah, I got it, of course. But you only stick around to get it if you trust the professor enough to give her the chance to explain it to you, and to give her a chance to let it sink in. The human equation has another important ramification. It defines not only what we're seeing, but also why we're seeing it. Every human being who becomes a scientist chooses to do that for reasons of the heart, reasons that reason does not know. When you're a scientist, there's nobody, watching you punch a time clock. You could goof off all day and never do any work. And until the end of the year, when you don't have anything to show for it, no one would notice. Why don't we do that? Why do we do the science? It's not to get rich. It's not to be powerful. It's not to attract girls. Didn't work for me. And the real problem is when you're a student, sometimes you forget why you're doing it and it just becomes a job. Some students go all the way into their PhD. What they're really looking for is the pat on the head from their professor. That gets old after a while. That's not going to sustain your career. Some people are doing it so that everyone will think I'm smart, because they're desperate to think they're smart, because deep in their hearts they don't believe they're smart. You find people who are hungry for acclaim in science, like the people who show up on television. I was on television. Watch out for those people. Why are they doing that? Not because they want to be scientists, but because they want to be known as scientists. On the other hand, you may just have that childlike sense of curiosity that sustains you through all of the long, hard slogs it takes to be a scientist. This is Buzz Aldrin, second man on the moon. Elder of the Webster, Texas Presbyterian Church, just up the road from the Johnson Space Center. When he went to the moon, he brought a chalice, which is now at that church, and he had communion on the moon. Presbyterian communion, not the real thing, but still. On the other hand, a contemporary of his, Carl Sagan, self-proclaimed agnostic. Sagan would not say he was an atheist. He said an atheist is somebody who knows more than I do. But nonetheless, he was someone who would not fake his data in order to be famous, because truth was more important to him even than acclaim, and he loved the acclaim. Truth was more important to him than getting on TV, even though he loved being on TV. Truth is an abstract. Truth is a transcendental. Truth is evidence of God. If you're worshiping truth, you're worshiping God. Truth and beauty, abstract concepts, words that religion uses to describe God, traits that allow us to recognize God, traits along with love and hope and faith, can't be measured, can't be weighed. But without those traits, we wouldn't bother to do the weighing or the measuring. In order to do science, there are 3 religious principles you have to embrace. Principles that not every religion embraces. First of all, you have to believe that there really is a universe, that I'm not just dreaming, that everything is not illusion. If you believe that, then there'd be nothing to study. You have to believe that the universe follows laws. If you didn't believe in the laws of the universe, you'd have nothing to recognize. Who was the first person who thought there were laws to be found before we had found any? In many ways, they were probably the theologians of the medieval universities who first systematically described nature, because it wasn't good enough to say Zeus did it. But the third and the most remarkable thing, you have to believe the one thing that's hard to get, congressional funding committees to believe is that it's worth it in and of itself. That pursuing something because it's beautiful is worth doing. That the universe is, in fact, good. That the physical universe is not full of traps that are going to lure you. Chocolate. Watch out for chocolate. Tool of the devil. It will lead you to obesity. It will lead you to acne. Abuse of chocolate will do that. But chocolate itself is a source of joy, and joy comes from God. It's evidence of the goodness of our Creator. You could have either of those attitudes. The Christian attitude is the one that said, our universe was created by a God who at every step along the way said, this is good. Our universe was created by a God who so loved the universe that he sent his only Son. Our universe is created by a God who also created us so that we can look at the sun and say, sister sun, brother sun, sister moon. Chesterton had a marvelous phrase looking at that wonderful prayer of St. Francis, the one that Pope Francis quoted. And he says, when you read Francis's idea of the physical universe, the ancients thought that Earth was Mother Earth, and Mother Earth was kind of scary. You best not fool with Mother Earth. But no, to Francis, the Earth was a sister. And not just a sister, a little sister. A little dancing, giggling sister that you love even as you laugh. That's the attitude that you carry with you to be a scientist and to be a Christian. Our ability to do science is tied to our ability to find and recognize that mixture of truth and beauty that we call elegance. Thanks a whole lot. And is it chocolate?
I'm spread.
Oh, thank you. It's a book. Even better.
It's a book.
It's a book.
Yes. A couple of things in there that
books are wonderful.
Celebrate our 90th anniversary that we're going to be acknowledging in 1926. So thank you so much for your time.
Thanks for having me here.
Oh.
Thanks for inviting me home.
Don't wait 10 years to come back. We want you back sooner. I also want to thank Cranbrook and the staff here. They were very kind to allow us to use their facilities so that we had enough room for all of you. Manresa is a beautiful place, but we don't have this many seats. So I even was allowed to park in the director's parking space, so how much better can that? So thank you all again for coming. We hope that you will join us at Manresa many times. It's a beautiful place, and it's a wonderful community. And if those of you who are Manresa stalwarts see somebody to your side that you know doesn't belong to Manresa's community yet, introduce yourself and please welcome them and ask them to join us. So. Careful driving home, and hopefully nobody will get lost or rained out.
It's cold and rainy.
Yes,
and
thank you.
I've been up real early, and I've got to get up real early tomorrow. So, because if we started questions, we'd be here all night.
Oh, I'm sorry. I didn't even think about the questions. Apologize.
So anyway, if you have questions, buy my books. Thank you, everybody, for coming.
It was terrific. Thank you. Back to her.
Sure. Do you have a pen?